All right, we're going to be looking at 1.4a, properties of radicals. So we just finished with exponents and radicals. We're going to jump in. There's going to be a lot of connections, hopefully you see. But that's what we're going to take a look at. Just four objectives: identify roots in radical notation, simplify radical expressions, combine radical expressions, and then simplify rational number exponents. So let's just jump in. Topic one, roots in radical notation. So first off, a radical, you can see its form right here. What's made up of is the inside part, A, is the radicand. And now when we convert it over, it will be the base. And so there's, again, think of exponents. A is going to be the base as an exponent, but it's called a radicand when it's in radical form. And we got the radical sign. It could be a square root, but not always. It depends on what the index is. So the index represents what root we're going to be sort of evaluating for. So if there isn't a number for 2, it's implied that it's a 2. It's a square root. So if there's nothing there, it's a square root. Otherwise, it's going to be identified. So when we look at the definition of a radical, it simply says, look, if I take the nth root of a and that's b, that means I can raise b, because remember the double arrow means if and only if. That is true if and only if when I raise b to the n power, I get a. So you can see I wanted to show you this because I wanted to show you the connection between exponents and radicals. So there's a relationship there we want to be comfortable with. There's going to be two types of radicals we look at: even indices and odd indices. When it has an even index, we want to be very careful because it requires certain things to be true and solutions and what's inside the radicand. So we want to be very careful and slow our thought process down with even indices. We want to make sure that we understand that the result of a radical when there's an even index, so a square root, again, doesn't have a number there, but like a fourth root or a sixth root or something like that, the result of evaluating a radical like that must be positive. So we're not going to get negative solutions if all I'm doing is a square root or a fourth root or a sixth root, unless there's a negative on the outside, but just the radical itself. Even root of a negative is not real. So in other words, if I have the square root of a negative or a fourth root of a negative, those are not real. Those are going to be complex. And you might remember from earlier classes where we have an I, that we take an I out. So we're not there quite yet in college algebra, but it's coming. But right now it would not be real, so that you would identify it more like that. Now, when it's an odd index, more like a cube root or a fifth root, that one is much more free to get answers. There's less to be worried about and careful of. And so some of the things that we want to be aware of with the odd index is that whatever the sign is inside is going to be the sign of our solution. So if I have a cube root of a positive inside, then that means my solution is going to be positive some way. If I have the cube root, let's say, of a negative, now that's not going to be imaginary like it would be a square root of a negative. A cube root of a negative simply means my answer is going to be negative, because I can multiply three negatives, and get a negative. So when the index is odd, you can get negative solutions. So there is no imaginaries or complex when we deal with cube roots or fifth roots or seventh roots, just with square roots and fourth roots. So we want to be very careful with even indices. Take our time, make sure we look at it carefully. Odd indices, really anything goes. So let's dive in and look at some basic examples of evaluating these. So we got the square root of 0. Really what that's asking is what times itself twice, because even though it's not there, there's technically a 2 here. So what times itself? So I know you guys are probably already know what the answer is here, but it's sort of like having like a question mark and saying what squared gives me 0. In other words, that's really what it's asking. And so hopefully you know that the answer to that is 0. So the square root of 0 is 0. If we do the fifth root of negative 32, the first thing we want to do is we want to go, wait a minute, can I even do this? Is it real or not? If the index is odd, we're good to go. All that means, the fifth root of negative 32 means my answer is going to be negative. Now I'm done with the negative. Don't worry about it. And then what we'll do to figure out the fifth root of 32 is break down 32. And again, you may already know what it is, so just jump ahead in the video. And then 8, you'll see 8 so much that I go ahead and just put the 3 2s every time I see an 8. So we're putting things in groups of 5. That's what an index does, is it tells us what we're trying to put things in groups of. And so we're looking to see, do I have a group of 5 of anything? So 1, 2, 3, 4, 5. So I have a group of 5 2s, and I had nothing remainder because remember I broke down the 8, so that's not there. Broke down the 16, it's not there, and everything else was removed. So I don't have anything left over. So the answer is -2 for that answer. Looking at the third example, we have the cube root of -27/6. What you want to look at is sort of this individually. Like you almost want to look at it as like the cube root of -27. This is a property that we're going to investigate, but just even in your head, look at it more like this right now. And then ask yourself, okay, the cube root of a negative simply means my answer is negative, so I'm done with the negative. And then what cube gives me 27? That's how we address these radicals. And so 3 cubed gives me 27. Then we do the same thing with 64. What cube gives me 64? And you can break it down or you can trial and error, but the answer is 4, so -3/4. So everything's working out really nice so far. Looking at the last one, notice there's another negative, much like the second one we did. The difference, though, on this one is the index is a 2. When it's not there, it's a 2, so it's a square root, it's even. And when you take the square root or any even index of a negative, that thing is not going to be real. So there is no negative solution. That only works for when the index is odd. So that's where we're at, some basic examples to get us going. So we really need to sort of address, okay, when we're simplifying these radical expressions, how do I know when a radical is simplified? How do I know when I'm done? What do I need to fix in order for this to be simplified? So if you look here, it says the radicand contains no groups of roots. And so a great example of that is something like the square root of 16. That is not simplified. And the reason is that I can make a group of 4s. Remember, my index is a 2, so that means I'm putting things in groups of 2. So I can make a group of 4s there and take those out, and I don't have anything left because 16 I broke down and there's nothing else left. So that's what I mean by taking groups out. So if you have, let's say, something a little harder, let's say the square root of 12, and we break that down, it breaks down to a 3, a 2, and a 2. Okay, and we're putting things in groups of 2 because of the square root, so it looks like I can make a 2 come out. But notice that 3 stays behind because it didn't have a friend to leave the house with. So if you don't got a friend, you don't got a group to leave with, you got to stay inside the house. And so that would be our simplify. So anytime we can take groups out, we want to take groups out. So that's number one. Number two, the radicand contains no fractions. This is an easy fix. All we got to do is split the radical to make 2 radicals. And this is called the quotient property of radicals. So it's a property. That's what we said in math. You got to back it with a property. But if I had something like the square root of 1/4 type of thing, what we can do is we can split that up and then hopefully be able to simplify. In this case, it works out really nicely to 1/2. However, that does create an issue sometimes because let's say instead of 1/4, it's 1/3. And then when we split it up, we do get the square root of 1, which is nice. It's 1. But the square root of 3 doesn't work out nice. So that creates a new issue. And if you look at number 3, that's our new issue. There cannot be a radical in the denominator. So this right here is not simplified because there's a radical in the denominator. So hopefully you're asking the question, well, how do I fix that? So to fix the issue of having a radical in the denominator, what we do is the process called rationalizing the denominator. And we'll discuss that soon. We'll deal with it in 2 different scenarios. We'll look at rationalizing single terms and 2 terms. So those are the 2 things we've got to look at is rationalizing single term denominators, which is like the 1 over square root of 3, and 2 term denominators. We'll see those in just a little bit. Okay. The very last thing we don't do a lot with, this is a very minor thing. We'll see it, but the index needs to be as small as possible. So we'll discuss this issue with rational exponents. So it just simply means if I have an index, let's say of 4, okay, and so I don't have enough, like if I try to break it down and take any groups out, I don't have enough factors to take a group of 4 out. But there is a way to reduce, this is not a simplified radical, so there is a way to simplify that, and we'll look at that, and that would be reducing that index down. So I mentioned a property, the quotient property of radicals, that's this one right here, number 2. So we've already sort of looked at it. Number 1 is called the product property of radicals. And so it just simply means this. If you multiply 2 radicals and they have the same index, they have to have the same index. But if you multiply 2 radicals with the same index, All you really need to do is multiply the radicals together and put those underneath that single index radical. With quotient properties, we looked at splitting it up, but you also want to keep in mind we could also bring it back. So let me show you what I mean by that. If we had something like the square root of 2, let's say, and then the square root of 8, something like that, and this is the problem that was given to you, what we have going on here seems like a lot of, because the square root of 2 doesn't come out nice, square root of 8 doesn't come out nice. But if I go ahead and go in the other direction and stack them, now you may be like, well, wait a minute, you said no fraction underneath the radical. You're right. I'm only doing this because I recognize that maybe reducing it like this and then splitting it back up would make my life so easy, because it does. Now my answer ends up being 1/2. So remember, the properties don't work in just one direction. You can use properties in both directions. This is a little bit like power of a power with exponents. When you have a radical inside of a radical, you can multiply those exponents, and you would have, excuse me, not the exponents, but the index, multiply the indices, and you would have a new radical. So just look at 3 really quick examples. We have the cube root of 3x to the 6y squared. What I'm going to do is see if I can break any of this down. 3, there's nothing there, so the 3 has to stay because it doesn't have 2 other 3's to go out of the house. Now, x to the 6th, notice we have 6 x's here, and I'm putting them in groups of 3. So when we have a certain number of things and we're putting them in groups, that is division. So it's no different than me writing, I'm not going to do this on every problem, and you shouldn't either. It's no different than me writing 6 x's out and then going, okay, I'm putting them in groups of 3. So I've got, 2 x's, so x and x makes x squared. Way easier to, instead of doing that, simply take your exponent and divide by your index. And that will tell you how many you can take out. And so what we have is we have 2 x's. Now, what we have is also y's. Sorry. And so we look and we have 2 y's, and I'm putting them in groups of 3. And what you'll notice is that we just don't have enough y's. So sorry, you're 1 short. It stays inside, and we're done. That would be a simplification, taking groups out. Looking at the next one, we have a quotient property of a radical. We can split it up and then look to reduce. And this one actually works out really nicely. A lot of times you'll get to where you have to rationalize, but on this one, things work out. Now, I do want to address a little bit of the numerator at this point, but we end up getting x over 2. Now, technically, and it's because of trying to find problems that all works, but this is going to lead us into what's starred down below. So even though I have one more example, what we're going to talk about down here in the red is what I'm dealing with right here. I had an even exponent inside the radical. I have an even index. And notice that my resulting exponent is odd. If you go from an even exponent to an odd exponent, you'll want to make sure to put absolute values around that, because, and here's the reason why, is because we don't know what x is. It could be positive or negative. And raising a negative, let's say, because the negatives are our issue, raising a negative to a 4th power makes it positive. So our result, the 4th root of a positive, has to be positive. Well, if x was negative and I didn't have absolute values, I'd have a negative. The result of a 4th root would be negative. And we already talked about the result. If I go back a couple slides here, the result of an even index, the result has to be positive. So sometimes we have to force it to be positive when we don't know what it is. And that's what we do with the absolute value. Now, looking at this last one here, technically using this property here, you get the 6th root of 64 because it's 3 times 2. Personally, what I do is I just work inside out. So to be honest with you, most of you would probably look at this as well and just do the square root of 64, which is 8, and the cube root of 8, which is 2. So let me go back and talk to you a little bit more about this one right here with the absolute values. If you go from an even power inside the radical, okay, so like a 4, a 2, a 6, an 8, any even exponent, to an odd power, to an odd exponent outside. So you simplify it, and now your result outside the radical becomes odd. Your exponent becomes odd. If that's the case, and it only goes with even indices. So this whole statement is only when we're dealing with an even index. Remember I said you got to be very careful with those. An odd index is like a big hippie. Anything goes. You're good. Cube root of a negative, negative. Cube root of a positive, positive. The result can be positive, the result can be negative. It doesn't matter. But when there's an even index, we got to be very careful that the result is always positive. So this is sort of your formal definition here, not something that you're going to need to regurgitate. But what it's saying is this: if the n is odd, if the index is odd, then what we have is our answer is just, we don't need to worry about what our answer is going to be. It can be positive or negative. But if the index is even, okay, then we got to make sure that the result of this is non-negative. So we look at something like the square root of x squared, and a lot of students will just cancel and they get x, and they're not quite right, because x can be anything, positive or negative. And the result of a square root must be positive. We must guarantee that it's positive. Now, the reason we need absolute values is if I go from an even 2 to an odd 1, I need to put absolute values around that. And there's my simplify. Looking at the bottom one here, you can do this a couple different ways. You can either do negative 3 to the fourth and like rewrite this problem so that you have negative 3 to the fourth is 81, and then go from there. And that's perfectly appropriate. However, a lot of students will go, oh, the fourth root and the 4 are going to cancel. Now, again, it looks like the answer should be negative 3. Now, down here, we wouldn't get negative 3. We get positive 3. So it's like, well, why are they different? I went from an even exponent to an odd exponent. So I must put absolute values around that negative 3, which means it's 3. So the answer is actually 3 on that one. Now, when you do this sort of rule, even to odd exponents, the absolute value only goes around the factor that went from even to odd. So not everything, just the factor that goes to even to odd. Okay, so let's go ahead and look at some examples. Work quicker than me and then just check your answers with mine. That would be great. But let's look at the first one. We have the cube root of a negative. So how I start this is I go, the cube root of a negative simply means my answer is going to be negative. So now I can disregard that. Take 16 and break it down. 8 and 2, and I know 8 goes to 3 2s. We do that so often. So I can group a 2, but notice, that I left a 2 behind. Now, also, don't forget your index here. So that's a small thing, but you will not get credit on Hawks without putting the little index 3, and then you only get partial credit when you do it for me on a test, let's say. So make sure to have that. So we're done with the 16. We took the 2 out. We left this lonely 2 behind. Now 8. Now, remember, it's division. I have 8 x's. I'm not going to write 8 x's on the board. But what I'm going to do is I'm going to take 8 x's and divide by 3. I'm going to see how many groups I can make. And what you'll notice is you can make 2 full groups. So 2 full groups of x's means I can take an x and another x out. So how we write that is more like x squared. So here, what we have is our quotient represents the exponent, how many we can take out. The remainder tells me how many x's have to remain. So I have 2 remain. Sorry, there's not enough to make another group. And so we're a little short. It's got to stay inside the house. We look at y to the fourth, okay? And so again, what I do with the exponents is I take 4, I divide by 3. And what I do is I say, oh, I can take 1 full group out of y's, but I left 1 y behind, kind of thing. The last thing is, do we need to worry about any absolute values? Even if we somehow went even odd, okay? We didn't, but, well, we did from y's. We went 4 to 1, we went 8 to 2, but here we don't need absolute values. And so the question I pose is why? And the reason is this. The index is odd. It's a big hippie. Anything goes. You don't need to worry about absolute values when the index is odd, only when the index is even. So speaking of an even index, let's look at the next one. It's a square root. So we break it down, 3 2s again. We can take a 2 out, and then we left a 2 behind. So take a 2 out, and then I left a single 2 behind. Then we got x to the 6. So I'm going to take 6 and divide by my index. Looks like I can take 3 full groups out with none left behind. So I can take 3 full x's out, and I left no x's behind. Do I need to be careful on one like this? Absolutely. And the reason is the index is even because there's a 2 here. It's not there, but it's there. So did I go from even inside 6? Yes. To an odd outside? Yes. So I must put absolute values. And what I put absolute values around is just the item that went even odd, which is just the X. So I don't need it around the 2. It'd be redundant to do that anyways because 2 is positive already, but you wouldn't want to do it um, uh, for any other variable unless that variable went even to odd. Looking at the last one, I'm going to split this up. So using the property of quotient property of radicals, and then really it's like doing 2 problems here. So the bottom one is a cube root of y cubed. That one, the cube root and the cube cancel. I don't need to worry about absolute values because it's a cube root and it's a big hippie, anything goes. For the numerator, what I got going on here is if I break 72 down, I definitely know it goes to like 8 and 9, and 8 goes to the 3 2's, and 9 goes to the 2 3's. And so I'm putting things in groups of 3, so it looks like I can take a 2 out, but I did leave 2 3's, which is a 9 behind. I didn't have enough 3's, so I got to leave that 9 behind. Notice I don't have enough x's to take out either. I only got 2 of them, and I need 3, so I got sort of a space there, but you don't need it. But that would be your answer for this one, 2 cube roots of 9x squared over y. Okay, I had mentioned something. One of the ways of knowing if a radical is simplified is this idea of there shouldn't be any radicals in the denominator. So how do I fix if let's say there was a radical in the denominator? And this process is called rationalizing the denominator. So we're going to look at the 2 different types, the single term and the 2 term. So the first one is the single term. Now, what you've probably learned up to this point is something really basic like this. So I'm just going to throw it out there. So it's like, well, I need to rationalize. So you'll multiply by whatever the denominator is. That's usually what I hear from students. And so what you end up getting is you end up getting the square root of 2 on the top, and then the square root of 2 times square root of 2 is 2 on the bottom, because this is square root of 4, because you just squish them together. And square roots work like that. Square root of 3 times square root of 3 is 3. Square root of 5 times square root of 5 is 5. Square root of a times square root of a is a. And so here, square root of 2 times square root of 2 is 2. So that's how you guys have learned. And most students usually do really well with those. But that's not always what the case is going to be, is it's not always going to be a square root. And so that works great for square roots every time, okay? But what if the index is a 5? So like this example here, it doesn't work the same. And so I don't want you to just fall in the trap of going, oh, whatever the denominator is, I multiply that. I need you to ask yourself a question, and then you hopefully can get an answer. So you're going to question yourself and then answer yourself for a problem like this. So when we split it up, this is where we're at. Now, first off, I have the 5th root of a negative. So I go, well, is that even possible? The index is odd. The cube root, the 5th root, any odd index of a negative simply means my answer is negative. 4, I don't have enough numbers yet. I may get some later, but right now I'm just going to leave everything sort of as it is. So even though I can take some x's out, I'm just going to leave it like that. And let's see what happens, because I need to rationalize the denominator. Okay, so to rationalize the denominator, what I need to do, so I'm going to get rid of that for right now. I'll put it back up there, is I look and I am going to ask myself the question, what do I have and what do I need? Okay, so I don't want the radical to be here, so I want to make sure I have a perfect set of 5. So 5, 10, 15, 20, any multiple of 5 would provide a perfect set. So when I look at 8 and I break it down, notice I only have 3 2's. So I don't have enough. So the question is, what do I have? 3 2's. What do I need? I need 2 more. So I have to multiply by the same index, otherwise I can't multiply. But I'm going to multiply by 2 2's, which is a 4. I'll show you why. See the 2 2's there? Then I do the same thing with a y. I say, what do I have? I have 2 y's. Okay, but I need a group of 5, so I'm short. So the question is, how short am I? Well, you be careful. Don't answer that out loud at home. Okay, so y squared, I have 2 y's. What I'm missing is I have 3 more y's. So no short jokes here. And so I've got 4, and whatever you do to the bottom, you got to do the top. Okay, so that's where we're at right now. So now what I can do is I can sort of simplify the top by multiplying, and then I'll end up like making this look a little prettier. So x to the 6 y cubed. Now in the denominator, what was I trying to make groups of? 2, okay, and then a y. Now, to prove that to you, 8 times 4 is 32. So I just want to make sure you guys understand where I'm getting this. Y squared times y cubed is y to the 5th. So if I go ahead and multiply those two together, what you'll notice is I can break these down and I end up getting 2 and a y. And so that's why it's just, and it's maybe a little easier just to ask, what was I trying to make groups of and how many groups did I make? So I rationalized the denominator. I made something irrational rational, and that's called rationalization. Now I can go ahead and finish everything off. I knew we can take a negative out. 16, if you break that down, unfortunately, you only have 4 2's. So we don't really have enough numbers. We do have enough x's to take out an x, but I did leave an x behind because 6 divided by 5 is 1 with a remainder of 1. And then definitely I don't have enough y's. I only got 3 of them. And then you got 2y on the bottom. There's our simplified. So that's simplifying a single term. What do I have? What do I need? What do I have? What do I need? Two terms a little bit easier in my opinion because you don't have to think too much. You don't have to ask yourself questions and give yourself answers. What you want to do is if there's two terms, you simply use the conjugate. Okay, now the conjugate of a plus b is a minus b. The conjugate of a minus b is a plus b. So in other words, and you did this maybe even in grade school. They may not have called it that, but this idea of a conjugate, 4 plus 3, the conjugate of 4 plus 3 is 4 minus 3. So it's not the opposite, okay, because these do not equal each other, okay? They don't equal each other. They're not opposites of each other. They're called conjugates of each other. So when it's a single term, what do I have? What do I need? When it's two term, no brainer, just use the conjugate. So the conjugate of the square root of 7 plus the square root of 3 is the square root of 7 minus the square root of 3. And whatever you do the bottom, make sure to do the top. Okay, now in doing this, what we want to do is we're going to distribute or FOIL in the numerator. So we got some stuff. I'm going to do it up here just so there's a little bit more room to write. And so what we end up having here is 4. Now, I can't multiply the 4 and the 7 because one's in a radical, one's not. So I just have 4 square root of 7 minus 4 square root of 3. And I may even need to leave that 4 out, to be honest with you. Let's do that. Actually, I think it's going to help. So before you distribute, let's see what the bottom looks like first. Get my parentheses looking a little better there. So the denominator. Now, what you need to remember about this, you can FOIL, okay? So I want to make sure we remember. So first, outer, inner, and last. So that's the FOIL. It's this distributive property. Now, when we FOIL, I'm going to do that right up here. What we get is the square root of 7 times the square root of 7, which is 7. Radical square roots work like that. So square root of 7 times the square root of 7 is 7. Then what I get is negative square root of 21. That's the square root of 7 times negative square root of 3. Then I get positive square root of 21. That's the inner. And then my last is square root of negative, so positive. So don't forget positive times a negative is negative. And then square root of 3 times square root of 3 is 3. So this is what I want us to focus on right here. Do you notice that the outer and inner cancel each other out? That is what makes a conjugate so special. 100% of the time, the conjugate is going to cancel out the outer and inner every time. So instead of doing all of FOIL, what you need to do is just FLE. So instead of FOIL, the outer and inner we don't need to do. All we got to do is floor to this thing. FLE. So first and last. This only works when you have conjugates. So you can't do this all the time, just when you have conjugates. So the square root of 7 times the square root of 7 is 7. So in other words, we're just not doing this because we understand what a conjugate does. So we don't need to do more work than we need to. So what we get is 7 minus 3 or 4. And this is what I said I'm glad I waited, is because now these 4's can cancel their common factors. and we're left with this as our simplified expression. Now, once in a while, you may have to rationalize the numerator, and that's a little new for most of you. We do it a little bit in calculus for simplification purposes, but here, don't overthink it. It's just if it's two terms, which it will be if you have to rationalize the numerator, we're going to use the conjugate of the numerator. Now, when we're done with this, you're going to have a radical in the denominator, and that's fine. That's what you should have. So don't try to rationalize again because you'll go back to the original problem. So it's two terms, so we use the conjugate. I'm not going to distribute the -4 just yet because I may be able to simplify. So I don't know. We're going to find out. So I sort of leave it outside for right now. In the top, knowing that they're conjugates, I'm just going to flood this thing. So square root of 5 times square root of 5 is 5. Negative times a positive is negative, and 3 times 3 is 9. And look what we got. Imagine that. -4, and we got that -4 on the bottom, and the square root of 5 plus 3. Canceled the -4s. Now be very careful. Our answer is not going to be just the square root of 5 plus 3. What else are we missing is that 1 on top. So remember, there's still a 1 here, and so we get the square root of 5 plus 3. So don't try to rationalize this. This is what you're probably used to rationalizing because you'll just go back to the original problem. Okay. Just looking at some overall review of what we've been doing and pulling some problems that are, that you may see in college algebra. So here what we have is we have the cube root of x to the 18. So what we want to do is see how many groups of 3, we can make out of 18. So 18 divided by 3 is 6 full groups with no remainders. 15 divided by 3 is 5 with no remainders, and 21 divided by 3 is 7 with no remainder. So we have nothing remaining still in the radical. Now, do we need to worry about absolute values? I'm going to circle something there. Hopefully your answer is no, because it's a cube root, it's a big hippie, we're done, no worries. Okay, even if we did even odd, doesn't matter. Okay, looking at the next one, it looks crazy. Okay, it's not, it's actually one of the easier ones. All you've got to do is just start and do the square root of 16. Okay, ignore the cube root part at this moment. The square root of 16 is 4. Okay, now let's go here and do the 4th root of 81. So you may have to break down 81, and what you'll find is it breaks down to 4 3s. So we can take a 3 out, and I left nothing behind. Now here, the cube root of a negative, now we have a minus sign, so I'm going to put that right now. So we have that minus sign, but the cube root of a negative simply means my answer is going to be negative, and then I can get rid of the negative, and the cube root of 1 is 1. So now what I have is I have the cube root, get a better 3 there we go. Cube root of, let's see, 3 plus 4 is 7, and then double negatives make another one, so we get 8. Oh my goodness. And then the cube root of 8 breaks down to be a 2. So that works out really cleanly. Looking at the very last one for this lesson, we cannot have a fraction inside of a radical, but that's an easy fix. You split it up, called the quotient property of radicals. Now, in doing this, there's a good chance we may have to rationalize because we may have a radical still in the denominator, which we do. So the question is, what do I have? What do I need? Because this is a cube root, I can't just multiply by another cube root. It doesn't make a full group. So notice I have 1 3, so I need 2 more 3s to make a group of 3. That's what my index is. So I'm going to multiply by a 9 because 9 breaks down to 2 3s. Now x's, notice I have 2 of them. Not quite enough. I need 1 more. And then whatever you do the bottom, make sure to do the top. So I'm going to simplify the numerator by multiplying those 2 together, and then we'll look at simplifying it in just a moment. So the cube root of 45, I think that's going to be okay. X and then y to the 4th. I think the y's will be able to take out. And then on the bottom, what was I trying to make groups of? Well, keep in mind, we had 2 3s there. I'm going to move it over here. So there's my group. I can take a 3 out, and I had enough x's to take 1 x out. And it's a cube root, so we don't need to worry about absolute values or anything like that. You can try to break down 45. It breaks down to 9 and 5 because that's where I got it from, and 9 only goes to 2 3. So 45 is sort of staying there. X is staying there. Looks like we can take 1 y out, but we have enough to leave, and then don't forget your index, enough to leave 1 y behind. So it looks a little bit like this. in 3x, and there's no vertical we can't touch the stuff inside with things that are not inside, so there's no vertical cancellation anywhere there. So that wraps up our lesson on 1.4a, properties of radicals. We'll still be doing some more radicals in 1.4b, but this will get you far enough to be able to start working on this material.